Hello, everybody. This is Sphere Break Defense Commercial Applications Group. Our team consisted of Ben Ruland, Connor Best, and Jaydon Warnick, and we were headed by our advisor, Dr. Nancy Studi. A little bit about our sponsor, Sphere Break Defense. They're located in Erie, Pennsylvania, military owned and operated, with a three-member team being the CEO, Aaron Lewis, Joe Fiore, the new VP of R&D, and Jason Pinta. They hold a patent, the ISO 9001, on the Sphere Break technology. They're sponsored by the U.S. Marines, and some of their applications include the ACV, or an amphibious combat vehicle, seen there in the top right, the Striker, the MTVR, and the MTVA 1P2.
Going into the technology background, the compact design was developed by Sphere Brake Defense. Instead of traditional rotors, it uses spherical ones instead, and it matches the curvature of the rotor with the four spherical brake pads that are on the two calipers. And the big thing is here is it has a toolless pad change technology. Our need was to research and pursue an additional application that the sphere brake technology can be applied to. And the problem was that the sphere brake defense lacks the ability to sell their product outside of their hydraulic market without system redesigns. So that's why we chose the pneumatic route.
The company came to the team with the following constraints: that the application must have a rotational component, must target frequent maintenance, must be in a competitive market, as well as must integrate into application easily. Through these constraints, the criteria were determined as that the maintenance efficiency must be maximized, the environmental resistance must be maximized, and the market differential must be minimized.
The application we ended up choosing was a 2024 Bluebird All-American FE school bus. Two of the main reasons were practicality and availability. We felt that with the sheer number of school buses in the world, that the patented technology Sphere Brake has come out with would be very well used on it, especially with mechanics and technicians. Also, the availability of getting into a school bus garage. A member of the team's family, Matt Nelson, allowed us to get into a school bus garage and see up close and personal of what was going on with these systems. Also, it met very closely with the criteria constraints we were given from the sponsor, and it fulfilled the need of moving away from the hydraulic sector. Our team's research led us to our initial conclusion. The application cannot work with the sphere brake technology as it stands. Why is this? Well, looking at pneumatic systems, a school bus typically runs from 60 to 120 psi, and is typically and usually governed at 100 psi. This is the input pressure the bus applies to the brake. And we learned in MET 432, fluid power, that the maximum safe operating pressure of an air system runs between 115 to 145 psi, but can be exceeded with high pressure systems that can reach up to 600 psi. Now, the issue: our design required 882 psi to function and match the force that needed to stop the bus within standards. After this discovery, we chose to shift our focus from making the brake be pneumatic to making the brake cheaper, which would still align with our scope. Before moving to material changes, the group want to list some possible solutions. Now, to get this technology put on a bus, we would need to integrate some sort of mechanical advantage. That 882 psi calculated is far too unattainable by the 100 psi system already found on the bus. Now, to get this, we would need some sort of, like I said, mechanical advantage. And three were talked about: the lever and wedge, the air-to-air intensifier, and the hydraulic intensifier. Both the lever and wedge and the air-to-air intensifier require significant redesigns of not only the caliper but also the piston on the current technology Sphere Brake has to offer. Um, they did want us to pursue this further in this semester. Unfortunately, with time constraints, we could not do it. So we do hope that a group in the future does come forward and do it, as it will be interesting to see if they can make it work. From here, we do think that the hydraulic intensifier is your best bet if you would like to put this on a school bus as soon as possible. This would use a master cylinder, which is technology typically found on your passenger car, like a Honda Civic, and it would use this by instead of a diaphragm pushing on the master cylinder, the air brake chamber would push on the master cylinder. This allows the system to still be utilized all the way up to there, but further, like the S cam would be taking out, and then the steer brake would be put in. This allows the system to use that hydraulic fluid, which can be compressed a lot further, and the pressures can be a lot higher to meet that force output that we need to stop within standards. Now, you might be thinking, why would we do a hydraulic intensifier if the company wanted pneumatic applications. Well, they asked for commercial applications and not just pneumatic, and we did come up with pneumatic, but the hydraulic would be still considered within that scope.
The material selected can be seen. The spherical rotor was determined through multiple performance indices to narrow down selection for the material. The caliper, piston, and strength hoop were determined by matching mechanical properties of the new materials with the current brake materials.